All right, guys, on to the photoelectric effect. So I have a metal plate, metal surface, and I've got light coming in, okay? Lambda comes in and kicks off electrons, and electrons end up traveling this way. And they have, the most energetic ones have what we call Ke max. So the energy contained within the light, the energy of the light is given by hc over lambda as per Einstein. Now, depending on what kind of metal you have here, like copper versus aluminum versus whatever, there is, there is the electrons sit bound to the metal depending on the metal. So something called the work function, which is the amount of energy you need to pry an electron out, right? So basically, the energy coming in, hc over lambda, has to go into getting the electron out, okay? Phi electric is the work function of that metal, and that's specific to the metal, and that's a constant, plus whatever is left over goes to give me the kinetic energy of the most energetic electron, okay? That happens on a incident basis, like, whenever you have an event, you have a photon come in, kicks off an electron, and the maximum kinetic energy the electron can have is Ke max. Okay, some of them will have less energy than that, but we're looking at when you apply and how do you measure Ke max? Well, we said that you run the electron through a potential difference of delta V. Okay, this is positive, this is negative, and when it doesn't make it anymore, you know that Ke max is equal to E times V stop. Okay, that's from electromagnetism, electrostatics. Okay, so let's say now that somebody tells you that you have a metal where you are using 620 nanometer. Okay, let's talk about these constants first. What are these, constants that show up here, or symbols that show up? H is Planck's constant. It's 6.63 times 10 to the power minus 34, and that's joules seconds. C is the speed of light, 3 times 10 to the power 8 meters per second. And this is the SI system, right? Not the best system to do this stuff in. I'll introduce another system shortly. Lambda is measured in meters, and all energy, phi electric, is given in joules. Okay, so is Ke max. Okay, the charge of an electron, E is equal to 1.6 times 10 to the power minus 19 coulombs. And let's see if we can do a quick example, with the photoelectric effect. Let's say that you shine light, lambda is equal to 620 nanometers, and you find that the stopping potential, so you have electrons being kicked out, and it takes 0.6 volts to stop them. The question is, what is phi electric in this case? Okay? So using this equation, we say what? H C over lambda is equal to phi electric plus Ke max. And H is, well, I know this is messy, 6.63 over minus 34 joules seconds times 3 times 10 to the power 8 meters per second divided by lambda, which is 620 times 10 to the power minus 9, because we're in nanometers, we need to be in meters, is equal to phi electric, that's measured in joules, plus, now what is Ke max? The maximum kinetic energy, Ke max, is equal to what? In SI system, it's the charge of the electron, 1.6 10 to the power minus 19, multiplied by the voltage, which is 0.6 volts. Okay, so phi electric plus this 1.6 10 to the power minus 19 multiplied by, we did the calculation here, we don't need this here, times 0.6, and this is coulombs, and this is volts. Okay, so on your own, just punch out, take a pause right now, take a stop, take a, not a break, but pause the video and see if you can come up with a value for phi electric in joules. All right. So that was the SI system of units. I don't recommend you do stuff in modern physics as much as you can using the SI system of units. For this part of the course, this is what I'm going to introduce now is a much better system. Okay, it was designed to, for small energies, or quantum energies. It's a lot better. HC. Okay, H was this messy 6.6 feet, 10 minus 34. HC in this system of units, EV nanometer system of units, this number is an easy 1240 EVs nanometers. Okay, all right. Now, lambda is measured in nanometers, and energy is measured in phi is in EVs. What's an EV? It's an electron volt. What's an electron volt? An electron volt is, okay, if you accelerate an electron through 1 volt, okay, it'll, by the end of it starts here at rest, let's say, starts, make this negative here, okay, and I'll make this positive this time around, and electron starts here. By the time it gets to here, it has a kinetic energy KE, and the kinetic energy of the electron, by the time it gets to the end, when it's accelerated through, the 1 volt potential difference is equal to the charge times the potential difference. And okay, so in the EV nanometer system of units, the energy of an electron that's been accelerated through 1 volt is equal to 1 EV. Okay, so what is the charge of an electron? Is 1. Charge of an electron is 1 E, okay? And the unit of energy is EVs. I mean, how does EV compare to joule? Okay, so if the electron has an energy of 1 EV after having accelerated through 1 volt, how does that compare to joules? Well, an EV is 1 electron charge, 1 electronic charge, accelerated through a potential difference of 1 volt. Okay, so what is that equal to? 1 EV is 1 E charge is 1.6 10 to the power minus 19 coulombs multiplied by a volt, and that gives you 1.6 times 10 to the power minus 19 joules. So what I'd like you to do now is that work function that you just calculated a few seconds ago, a few minutes ago, phi, you got it in joules, get it in EV is equal to what in EV. And how do you do that? Well, you do the conversion. If you have an EV, that's a joule. If you have a joule, yeah. So you have it in joules, convert it to EVs, and see what you get. All right. So in this system of units, let's do this calculation, using this system of units. I've got, the wavelength is still 620 nanometers. So how does this work here? We say that HC over lambda is equal to phi electric plus KE max. Okay? And HC is this nice number, 1240 EVs nanometers, divided by lambda, which is 620. You see why I chose 620 now, is equal to phi electric plus KE max. KE max is the same as EV stop, okay? So this equation can be written as HC over lambda equal to phi electric plus EV stop. So either or. KE max is the same as EV stop, 0.6 EVs, okay? So what is phi electric? Well, that number is now, it's an easy, 2 EVs equal to phi electric plus 0.6 EVs. So phi electric should be 1.4 EVs. That's the work function of that metal. That's how much energy it takes to get an electron out. So what happens when your light coming in does not have that much, the right wavelength, okay? So let's say that you have, let's do this calculation, this discussion here on the side. If you have a metal, right, a metal surface where phi electric, let's say, is equal to 3 EVs, okay? And you got light coming in, and lambda is equal to 620 nanometers, okay? A question would ask you, what is the stopping potential? You're like, okay, Pause for a second, pause this video and think about it. What is the stopping potential when I have something like that? Well, you say, okay, well, let's see. I mean, the energy it takes to get an electron out is 3 EVs. What is the energy contained in these guys? The energy contained in these guys is hc over lambda equal to 1240 divided by 620. These photons only have 2 EVs of energy. They are not gonna, no photoelectric effect is gonna be produced here. Right? So there is no stopping potential. Then you have to actually apply a reverse potential to get the electron out, which is doable. Right? So now then, what wavelength do you need to get an electron out of a metal with a work function? It's called the cutoff wavelength. Okay? How does that work? Well, the cutoff wavelength, h over lambda cutoff, okay, lambda cutoff, right, is is equal to phi electric, right? So I think it's double T. So hc over lambda cutoff is phi electric. So lambda, the biggest lambda, anything bigger than that is going to render you with less energy than you need to get the electron out, right? So phi electric is equal to, the lambda cutoff in this case is equal to, what is phi electric? It's 3 EVs, right? So hc is 1240, right, divided by 3. You have to have at least, or at most, 413.33 nanometers to get the photoelectric effect to work in this case. Okay, we're going to pause here and continue with the next part of monophysics.